Welcome to DAT322. I'm Brad Beebe. I'm the general manager for Amazon Neptune. And today I'm also joined by Ian Robinson.
Hello.
A principal graph architect. A little over 6 years ago, I joined AWS from a small open source graph database company to launch a managed graph database service. And in 2017, here at reInvent, we announced the preview of Amazon Neptune. Today, the deep dive into Amazon Neptune Serverless is one of the most popular database sessions here at reInvent. So I'm super excited to be here, and thank you all for coming. Before we get started, I just wanted to get a sense of the room. How many of you are using a graph database today? Cool. How many of you are using Amazon Neptune? Has anybody tried Amazon Neptune Serverless? OK. So today, we're going to peek under the hood of Amazon Neptune. I'm going to start with a quick review about graphs and some of the use cases, go into how some of our most recent features operate, help you understand how Neptune Serverless optimizes CPU and memory for you, and then we're going to show you a global serverless graph database cluster. And if we have some time, we'll take some questions. Graphs are awesome. And they're awesome because they allow you to innovate using the relationships in your data. By looking at those relationships, you can create new things and build new capabilities. There's really 4 things I'd like you to take away today about graphs. The first thing is they're a data model that's based on relationships. And in a graph data model, relationships are a first-class object. The second is that graph applications are about traversing those relationships, querying them, filtering them, asking patterns over them. The third is that processing graphs is hard. Graphs tend to have random data access patterns. If you think about starting at any particular node in a graph and going out a couple of hops, it's very hard to use the same kind of data processing techniques that you use to get good locality for your data in other kinds of data models with graphs. And lastly, if you have applications that need to do generalized graph processing, you really need to look at a purpose-built data store that's optimized for doing graphs. Amazon Neptune is AWS's managed graph database service. Neptune is designed for interactive graph workloads, for parameterized queries from 1 to 3 hops, to be answered within millisecond latency for graphs of billions or tens of billions or even hundreds of billions of nodes. And one of the things that makes Neptune very unique is that it gives you the most choice of graph data models and graph query languages. Neptune supports both property graph and RDF graphs and gives you 3 different query language choices. And in the fullness of time, we believe that these kind of differences will meld together because what we hear from customers is that they want to build graphs. And now, Neptune is serverless and global too. One of the coolest things for me about working in the graph space is getting to see all the things that you guys do with graphs. The customer use cases that you see are innovative, they're interesting, they're doing new things. And if you look at the customers here, you can see the use cases cross many domains, from financial services, life sciences, security. And every day, thousands of customers use tens of thousands of Neptune instances to power their graph applications. But it's still day one for graphs. If you think about the domain of customers who understand graph databases as we know them today, compared to the domain of customers who could benefit by using the relationships in their data, we're still very early. And this means that we also need to expand into different kinds of graph use cases: transactional graphs, OLAP graphs, graph analytics, graph machine learning, linked data. There's 4 particular use cases that we see within Neptune that are gaining traction. Knowledge graphs use relationships between data for information retrieval. Customers like Siemens are using knowledge graphs to build IoT and digital twin platforms. Identity graphs use relationships to relate devices or users or customers or employees to allow you to understand all the touch points that you have so you can track them across journeys, you can understand how to improve customer experiences. And customers like Cox Automotive have built identity graphs to help them improve the customer journey across the digital platforms that they operate. Fraud is a classic graph application. The only limits to detecting fraud are the creativity of those who perpetrate it. The kinds of fraud that you can detect with graphs, obviously, includes relationships, where you look at how things are related. Customers like Games 24/7 are using a graph-based technique to detect a type of collusion fraud that they found in their online rummy games that they weren't able to detect using traditional fraud techniques. And lastly, security graphs. Like fraud, security is also a classic graph application. What we see is customers using the connections in their IT resources, their user identities, to help understand and improve cloud security. Customers like Wiz, who are using graphs to help you understand, of all the threats, which ones are the most important to remediate. We've had a really busy year. We've launched new capabilities that expand the ways that you can use graphs, from machine learning to new query languages to multi-region deployments to serverless capabilities. And along the way, we've made 14 different engine releases to improve security, add new features, make bug fixes, improve availability. One of the things that we consistently heard from customers was that they wanted not only to be able to query their graphs and use the graph languages to understand their data, but they wanted an easier way. They found the value of the graph important, but they wanted to share it with others and broaden those who could get value out of it. So today, I'm announcing the AWS Graph Explorer. The Graph Explorer is a low-code web application that allows you to visually browse your graph using a faceted browsing model. It supports both the RDF and the labeled property graph models, and we'll be making it available next month under an Apache 2 open source license so that you can use it as part of your applications to help you with your graph needs. In 2020, we launched Amazon Neptune ML here at reInvent. Neptune ML was one of the first capabilities that allowed you to use graph neural networks, a type of machine learning, that's purpose-built for gaining insights on the relationship of your data. And what we heard from customers was that they found a lot of value in using GNNs to make predictions over their graphs, but that they also wanted to do it based on the latest data that had arrived. With transductive inference, which we supported before, you could only use the predictions that had been generated on a previous version. And so with the engine release that we made last week, we've now launched support for online inductive inferencing. This allows you to use the power of GNN machine learning models to be able to make predictions on the latest state of your graph. So if you imagine you have a graph and you want to use a security application or you want to approve a financial transaction, these kinds of predictions and using the latest state of the graph are very important. In May of this year, we launched OpenCipher. OpenCipher gives you a way to declaratively query your property graph. It interoperates with our existing Apache Tinkerpot property graph, so if you have a Neptune Gremlin instance, you can use OpenCipher on it right away. It supports the binary protocols that are often associated with Cypher applications, and it gives you a new option if you're using a Cypher application to avoid expensive commercial licensing for a fully managed Cypher-compatible graph database. Let's take a deeper look at OpenCipher and Gremlin. OpenCipher is declarative, which means that it's similar to SQL. You express patterns over your data, and then you retrieve the results. In here, we're expressing a very simple pattern where we're starting for one airport, Anchorage, which is the airport code ANC, and we're looking for all of the airports that have one direct route from Anchorage. And that's what that Cypher query says. And so if you have developers who are familiar with declarative languages, OpenCipher will seem very natural to them. On the right-hand side, we have Apache Tinkerpot Gremlin. Gremlin is an imperative traversal language. It's more like a programming language. It allows you to explicitly express the traversals that you want to make over your graph. And if you look at the Gremlin snippet here, you can see we're starting with the graph, the g.v. We're finding a vertex that has a property of the airport code, and then we're hopping out and returning all of the results. And so Gremlin can be a very powerful tool to do fine-grained traversals. But the learning curve with Gremlin can be steeper. And so, again, in the fullness of time, we really see the need for both. Sometimes you want a declarative model to interact with your graph, and sometimes you want very fine-grained control. OpenCipher is new, and it wasn't just launching a new query language. We also launched a new query engine, something that we call DFE, or the Data Flow Engine, which represents a multi-year investment in query performance. And so we're iterating very quickly. And so if you're using and developing with OpenCipher, I highly recommend that you keep up with the latest engine releases. Also in last week's release, we released important performance improvements for variable length path queries. You can see some of the latency and throughput improvements on the right-hand side. And we also added new functionality for user-specified IDs, something that was blocking customers that wanted to migrate from other Cypher applications. And so I would say, don't be a stranger. Let us know. I've included an email address here on the slide if you're interested. Please do reach out. We also heard that people wanted multi-region capabilities. And they wanted them for disaster recovery and also low latency applications. And so we launched Amazon Neptune Global Database. And to understand this, I want to take a quick review about Neptune clusters. And so the core of Neptune is a purpose-built storage engine that's durable in ACID and provides immediate consistency. And it does scale-up query evaluation. and it has a scale-out storage service. When you create a Neptune cluster, you create an instance of storage that's shared between up to 16 different nodes, one being a primary writer, and up to 15 different read replicas. That shared storage service provides multiple availability zone high availability. It provides your durability. It automatically scales in 10 gigabyte increments. And as of this year, it supports a total segment size of up to 128 terabytes, which in graph terms translates into a graph of somewhere between 200 billion and 400 billion nodes, edges, and properties. One of the features of the storage layer is that it supports high availability. So if you have a writer and the writer's not available and you have a reader, that reader can instantly swap over, change roles, and become the primary writer. So imagine for a moment that rather than having a read replica in an availability zone, you had a whole region of read replicas. And if you can do that, you can understand Amazon Neptune Global Database very simply. With Amazon Neptune Global Database, you have secondary clusters that operate in other AWS regions. The storage service also provides low latency data movement between the regions. And there's some new CloudWatch metrics that you can use to understand how much data is moving and how it's being replicated. Neptune Global Database supports up to 5 different secondary clusters. And each cluster, if you go back to the read replica analogy, removes one of the available read replicas in your primary cluster. So in a normal Neptune cluster, you can have up to 15 low latency read replicas. If you have one secondary cluster, you can have 14, 2, 13, so on and so forth. There are 2 failover modes supported with Neptune Global Database. The first is a planned failover mode, which you can use if you want to rotate between regions. And the second is an unplanned failover, which allows you to detach and promote a cluster to its own region. I want to go through a couple of backgrounds about scaling queries. And so if you think back to the storage layer and the instances, you can look at how Neptune evaluates queries. So we use a scale-up model. As you issue Gremlin, Sparkle, or OpenCipher queries, those queries are processed using the CPU, RAM, and memory resources on the instance. Each query comes in, the query is parsed, we generate intermediate representations, ASTs, we generate logical query plans, we generate physical query plans, we execute them. All of that generates CPU and memory usage. One of the things that we have in the instances is a buffer cache. And a buffer cache is a part of RAM in the instance that stores the pages of your graph data from the storage layer. And as you execute queries, those pages are read into the buffer cache and used to evaluate them. If you execute a query and you have a cache miss, that means that to give you an answer, we need to read that page from the storage layer, which has a cost of latency. So you're going to see increased latency. And if you've ever tried a system and issued a query, and then you've issued the same query again and it's been much faster, you have this sort of cold start problem. And this is why this happens. If you have a query that's almost fully addressed by pages that are already in memory in the buffer cache, then you'll see a much faster, much lower latency query. Neptune provides you some tools for you to be able to understand this behavior. So the blue data series that you see is the buffer pool cache hit ratio. The orange data series is the volume of read operations. So this represents read operations from the instances to the storage layer. And if we look at the beginning here, we can see that there's a relatively high buffer pool cache hit ratio and a relatively lower amount of volume read IOPS. And if we move forward, we can see that the buffer pool hit ratio has declined, and there's a corresponding increase in read IOPS. And this is what we would expect if you think back to that buffer cache model, where you're issuing queries, they're not available in the buffer cache, that's causing you to go more to the storage layer. And if you see this cache hit ratio fall below 99.9%, there might be an opportunity for you to improve performance by adding memory into your instance. So the way you do that would be increasing your instance size. You can also use the same technique to find cost optimization pieces. If you see consistently that your buffer pool cache hit ratio is high, maybe you can lower the size of your instance and save money. And what we heard from customers was that doing the capacity planning and instance tuning to get this right was hard. If you over-provisioned your cluster, you spent too much. If you under-provisioned your cluster, you risked that at a time of peak workload, you wouldn't have enough capacity. And so about a month ago, we released the general availability of Amazon Neptune Serverless. Neptune Serverless automatically expands and contracts your capacity in response to the workload that you're providing to the server. And by using Neptune Serverless, you can save up to 90% of your cost versus provisioning for your peak workloads. Neptune Serverless has all of the same functionality for Amazon Neptune that you get for querying data, for loading data, for high availability, for durability, for global database pieces. It simply adds a new instance type that's called DB Serverless. And as you apply workload to DB Serverless instances, they grow and shrink based on the workload that you're providing. You can use these instances within any role of your cluster. You can have a cluster that's completely serverless. You can have a cluster that has serverless and provisioned instances. Serverless instances can be in the role of the primary writer. They can be in the role of the read replica. If you have instances that are serverless and writers and also in the replicas, and they're in tier 0 and tier 1, the system will automatically keep those serverless readers scaled to the same level as the writer. And the reason that it does that is to allow you to maintain the high availability and fast failover time. In the case that the writer becomes unavailable, you can immediately fail over to a reader that's scaled to the right capacity. And of course, it also works with Neptune Global Database. The fundamental unit of Neptune's serverless capacity is a Neptune capacity unit, or an NCU. An NCU represents 2 gigabytes of RAM and corresponding amounts of CPU and network bandwidth. When you provision, or when you create a DB serverless instance, you specify a minimum and a maximum NCU level. The minimum is the capacity at which the instance starts, and the maximum is your control. So it's the maximum that you want to allow that instance to grow. And as it grows, it scales proportionately in a predictable way. As you have larger amounts of capacity, it will scale up faster. As you issue queries and apply workload, again, think back to the buffer cache. You're using more CPU, you're using more RAM, you're using more network bandwidth. As you provide that workload, Neptune Serverless keeps track of what's going on in that instance, and it responds to increases in CPU utilization, increases in memory usage, increases in network usage, and it will allocate and deallocate Neptune capacity units in response to that. I want to show you an actual customer example. This is a customer cluster in Europe that was created just a few days after we launched the GA. The blue line, the data series, represents the NCU capacity units that the customer is consuming. And as you go through, you can see that we have a scale-up event. It scales partially up. Then you can see that we scale all the way to the max NCUs. We scale down again. It scales back up and scales all the way down. And if you look at this across time, you'll see that this is where the opportunity to save versus provisioning for peak capacity comes from. As you can see, there's only a very small amount of time during these windows where the customer is actually using all of that capacity. This is a chart of the same customer, but showing our internal metrics. And the different colors of the different data series represent pieces that we're instrumenting. So they represent CPU utilization, they represent memory utilization, they represent minimum and maximum NCU values. And by monitoring all of these pieces, that's how the scaling behavior within Neptune Serverless operates. When wouldn't you want to use serverless? Well, there's a couple of items. One is that the maximum capacity that we support today is 128 NCUs. This is roughly equivalent to the amount of memory and CPU in an R6G 8X large. The largest instances that Neptune offers today are an R5 24XL. So if you have a graph use case and you're already using a larger instance, or you have particularly memory-intensive queries, then your workload may not fit into the maximum size of Neptune Serverless. The other reason you might not want to use it is that you have a very predictable workload. If your workload is steady state and constant, you may find that using a provisioned instance is a better option. Like OpenCipher, Neptune Serverless is something we're actively working on developing and improving. We have some, in the very short term, AWS CloudFormation and Cloud Development Kit support is coming. We also will plan to support scaling down to smaller instance sizes. Today we support a minimum capacity of 2.5 NCUs, and we'll add support to go lower than that. Also expanding regional availability. And again, we'd love to hear from you about how you're using serverless and how you'd like to use serverless. And with that, I'd like to introduce Ian Robinson, who's going to show all of this to you. So thank you.
Wonderful. Thank you, Brad. Hello, everyone. So I've got a short serverless demo for you. But in showing you serverless, we're also going to look at some of those other big features that Brad mentioned. So global database, OpenCipher, and some of our open source productivity tools, including that Graph Explorer. We'll have a brief look at that Graph Explorer. So if we can just switch to the demo. The first thing you're going to see is me unlocking my machine. Okay, so I'll start by showing you how to create your own serverless database, and then how you can create a global database. Now, I've previously created my own global database cluster spanning 2 different regions. It's a global serverless cluster. And I've been running a reasonably heavy workload on and off against that for a few days. So in a little while, I also want to show you some more of those CloudWatch metrics that show how Neptune scales as we vary the workload. But before we get to those metrics, I also want to talk a little bit more about the workload itself, about the kind of data set that we're using, and some of the queries that we're issuing. And effectively referring back to one of those use cases, the fraud detection use case that Brad mentioned earlier. But I'll start by showing you how you can create your own Neptune serverless database. So if you're familiar with creating a regular provision database, then there are no surprises here. You can create a serverless database via the console, or using the CLI, or using one of our language-specific SDKs. And we've got CloudFormation support coming soon. So I'm going to create a new serverless database from the console. So I'll just click Create Database, and we get the regular workflow. So I've got a choice here, the radio button at the top. Let's just expand this a bit. I'll choose Serverless. And the engine version dropdown will now be populated with the engine versions that support serverless, which is our two most recent releases. So I'm going to choose the most recent release, 1202, and give the database a new name, MyDB. Okay, this capacity settings tab is where we can specify the scaling behavior of our serverless database. So as Brad says, Neptune serverless scales according to what we're calling Neptune capacity units, or NCUs. So here you can specify the minimum number of NCUs, for instances, in your cluster, and the maximum number of NCUs. The minimum we support today is 2.5, the maximum 128, which is that equivalent to an R6 8x large instance. So new instances or idle instances will typically end up with the minimum value here. Then as the load increases, Neptune will scale your instances, often in very small increments, often a half NCU increment. It will scale it as necessary, potentially all the way up to the maximum. And then as the load drops off, it will reduce the capacity. Okay, the rest of the workflow is pretty standard. I'm going to choose to create a multi-AZ deployment. So this is a regional database, but we'll end up creating a read replica in a separate availability zone. So a writer and a reader in separate availability zones. I'll specify I want to create a new VPC and click Create Database. So it's as simple as that. There's really not much to being able to create your own serverless database. Once you've done that, you may then choose to create a global serverless database. And again, this is very easy. Again, you can do it from the console or via the CLI or using the SDKs. I'm going to create a global database from the console here. I'll choose an existing database, an existing regional database. And just from the Actions drop-down menu here, I can click Add AWS Region. So this gives me the opportunity to give my global database a name. So we're incorporating a regional database. That will be our primary cluster within the global database. But we're giving the global database its own name, my global DB. And then I can begin adding additional clusters in other regions. And remember, those additional clusters will be read-only clusters, but I can have up to 5 of them in different regions from the primary. Okay. So again, being able to create a global database is very, very simple. And we can create global serverless Neptune databases, again, using all of this tooling. So what I've done previously is create my own global database cluster. So I've got a primary cluster in US East 1 and a secondary cluster in EU West 2 in the London region. So both of these clusters are serverless. They both have 2 instances. So the primary cluster will have a reader and a writer, and the secondary cluster has 2 read replicas. And then all that data is being replicated at the storage layer. What I've then done is create a simple serverless application using a number of Lambda functions that issue read and write requests. So read and write in the primary region and a read-only workload in the secondary region. And I'm driving those Lambda functions using a load generator. So that allows me to vary the load against the clusters. So I've been running this on and off for the last few days and driving the workload quite high. We'll look at some of the CloudWatch metrics for that in a moment. But before we do that, I just want to talk in a little more detail about the actual workload that I'm running. So what I've chosen to do is to incorporate one of our sample applications from our Neptune notebooks into this demo. So the Neptune notebook is an Amazon SageMaker hosted Jupyter notebook. You can provision them from the console again. There's a notebooks menu option on the left-hand side. And this allows you to create a notebook and associate it with your database. And those notebooks then allow you to write your own queries, to interactively write queries run them against the database, and if you want, also visualize the results. So it's a really nice development tool for data scientists or data engineers or application developers who are building out a solution and want interactively to develop some of their queries. I've got a notebook already running. When you first open the notebook, you can navigate your way through a number of different directories. The notebooks are also an open source project. So they're called Graph Notebooks. It's an open source project available on GitHub. So you can use them not only with Neptune, but with other graph databases. Any graph database that supports Gremlin or OpenCipher or Sparkle, you can use the Graph Notebooks with them. But I've got this one attached to a Neptune cluster. I'm going to work my way through these directories. So we've got lots of different tutorials, lots of sample applications. The one that I'm interested in is this one, building a fraud graph application on Amazon Neptune. So I've chosen to take the data set from this sample application and some of the queries and incorporate them into my serverless app. So this notebook is pretty typical of the sample applications that you get with the Neptune notebooks. It includes quite a comprehensive narrative that describes the use case. It has a sample data set that you can install. So a little further down here, there's the opportunity to seed your existing database with a sample data set. I've already done that, so I'm not going to run this cell again. But the notebooks also include a number of queries that illustrate the data model that's specific to the application scenario. And then there are a number of queries that implement key application capabilities. All right. So this is a fraud detection solution. And the domain here is relatively simple. The data set contains accounts, merchants, and transactions. So the accounts are credit cards. The merchants are companies that are offering products and services. And the transactions are instances of payments. When somebody with a credit card buys a product or service and makes a payment, that's a transaction. We're also capturing some additional contextual information around those transactions and around the accounts themselves. Things like IP addresses, email addresses, telephone numbers, physical addresses, and so on. And then some of the fraud detection queries are using the connections between this identity information, this contextual information, to identify potential fraud rings, so accounts that are linked together by way of shared bits of information, or to identify instances of identity theft. And that's all the stuff that we demonstrate in this notebook. And this is some of the stuff that I've incorporated into my app. So I'll just show you a few of these sample queries that you get with the notebook. This is a property graph data set. And in the first queries, we're using the Gremlin query language. So as Brad mentioned earlier, this is an imperative traversal language. This first query is simply showing you how we model an individual account. So you can see that we have a vertex. We're looking at a vertex that represents a specific account. And then we're navigating some of the relationships that connect it to pieces of identity information. So I'll run that query. We get some tabular results. But we can also, with the notebook, visualize those results. Okay. Ooh. So you can see we're modeling an account. At the center there, we have an account, which will have the credit card number, the name of the account holder, and then we're associating it with specific pieces of identity information. So we've got a couple of email addresses here. We've got an IP address, a telephone number, a couple of telephone numbers, date of birth, and so on. So that's how we're modeling an individual account within this data set. We have another query here that shows us what a transaction looks like. So again, for a specific account, we're looking up just one of its transactions. And again, I can author these queries in the body of the notebook, inside these cells. I can get a tabular representation of the results, but I can also get a graph view of the data, of the results. So, all right. And it tends to spring in and out very, very quickly. What we have at the center there is a transaction. It will have the amount, the date on which that transaction took place. It's connected to an account, and it's also connected to a merchant. And we've also captured some additional contextual information again. In this case, we've captured the IP address of the device that was used to make that payment. We have another query here, again, another Gremlin query that finds all of the transactions for an account. There we are. So we can see the account at the center there, and then we can see many instances of transactions, of payments that have been made, and the merchants to whom those payments have been made. Okay. So these first queries are simply helping you to understand the nature of the data model. But then there are other queries in the body of this notebook that begin to implement some of the more interesting fraud detection parts of the solution. So one of the things that we're interested here is in identifying fraud rings. A fraud ring is a group of people who share a pot of identity information, IP addresses, phone numbers, and so on. And they use that to open multiple accounts, multiple lines of credit. And then they coordinate their activities so that they max out those lines of credit, and simultaneously they then just disappear off the face of the planet with no intention of repaying their debt. So if we're modeling our data like this, we can often identify what may be potential fraud rings by looking at the connections that associate accounts by way of those bits of identity information. So if I'm interested in investigating a particular account and seeing whether it may be participating in a fraud ring, I've got a query here. Again, we're starting with an individual account. We're looking at the node that represents that account, and then we're navigating out into the graph to see whether there are other accounts that are connected by way of one or more pieces of shared information. And you can see here, I think we have about 8 accounts that in one way or another are sharing bits of identity information. So the larger this little connected group of accounts, the more likely it is that we're perhaps looking at a fraud ring. Now, with that query, we're just going one hop deep into the graph, looking at the ways in which those accounts were connected. We can go deeper. We can go 2 hops deep in, looking for transitive relationships between accounts. And that's what this next query is doing. But this time, I've chosen not to use Gremlin, but to use OpenCipher. So I've rewritten what was the standard query in this notebook and used OpenCipher instead. And this is simply to demonstrate that we can use these 2 different query languages, but against the same underlying data set. So OpenCipher gives us a very concise way of expressing graph patterns, and this OpenCipher query here is allowing us to navigate some of these connections between bits of identity information up to depth 2, really, in order to find the larger network. So again, we can see that these accounts are beginning to participate in a much larger, potentially fraudulent network. And having identified that network, we can then identify our exposure. You know, what transactions have taken place within this network recently? What's our potential liability here? And when I ran this, I noticed a few interesting things. Down here on the bottom right, there is an account and all of its transactions, and it's associated with all those other accounts by way of one piece of shared information, and that's the date of birth. Well, in a large data set, it's going to be quite likely that we'll end up with multiple people with the same date of birth. So my feeling is that that account down there and all of those transactions are probably quite legitimate. But further up towards the top of the screen, we have that denser network of accounts and all of their transactions, and that's the thing that we'd likely want to focus on. Okay. So as you see, the notebook gives us the opportunity to write the queries and visualize the results. So it's great for anybody who's familiar with the query languages and wants to iteratively or incrementally develop these kind of queries. But then we also have users, non-technical users, who don't necessarily want to use a query language, but they nonetheless want to explore the graph and share the results with some of their colleagues. And so that's why we've also developed the Graph Explorer, another open source productivity tool that allows non-technical users to examine or browse the graph. So you can search by way of specific entity values. I'm simply going to choose one account here and add it to the visualization. I can then look at the properties of that account. So again, we see the account number, the name of the account holder, and so on. And I can begin to expand the graph. I can look at the transactions for this account. Again, I can also have a tabular view of the data that I can download. I can take one of those transactions and expand that. Okay, so we're seeing the merchant, the IP address, and so on. So this allows me to interactively navigate the graph to search for entities based upon their property values. I can get tabular representation of results. I can download that. I can snapshot the screen. I can share these results with my colleagues. So this is something that we're currently developing, but we will be releasing it very shortly. So that's given us some insight into the kind of workload that I've been running against my global serverless database. As I say, I've been doing this on and off over the last few days, driving a reasonably heavy workload that simulates a day's worth of payments over the course of several hours. So we're just going to look at some of the CloudWatch metrics here for the primary and the secondary cluster. We'll look at this first one here. So what I initially did was bulk load some historical data into the primary cluster. And then after a little delay, I then ran the real-world workload, where we're driving read and write traffic to the primary cluster. So what we see here is the writer instance in that primary cluster. These are some of the details for the writer instance in that primary cluster. And we're capturing the serverless database capacity, the CPU utilization, and the number of gremlin requests per second that we're issuing. So at its peak, we were running about 2,500 requests per second. And that's about 2/3 reads, 1/3 writes. So here we've got about 600, 700 writes per second. On the left-hand side, we see this initial peak of CPU utilization. So this is when I'm doing the bulk load, issuing the bulk load through the head node. And that drives up the CPU utilization because we're using all of the worker threads to write in parallel down to the storage layer. So that CPU utilization is driving Neptune serverless to add more capacity units. So it adds them very, very quickly, and we end up with around about, I think it's 63 NCUs at the peak of that bulk load. All right? But once the bulk load is finished, it drops off very quickly. And the characteristic of this is we scale up very quickly, and we scale up very rapidly towards the end of that scale-up period, and then there's a stepwise cooling off period after the bulk load is finished, where we end up reducing the number of NCUs down to the minimum of 2.5 again. And then a little later on, we actually run the full-blown workload. And at that point, we're getting about 600, 700 writes per second. And this, again, is driving some CPU utilization because we're using lots of worker threads to service all of those requests. So what you see here, the bottom two lines here, is the capacity units, the NCUs, and the CPU utilization mirroring one another. All right? So it's about 600, 700 requests per second at its peak, and the CPU utilization is effectively determining how we're scaling. But you can see even at the peak here for the write workload, we're only using about 20 NCUs. This is out of a maximum of 128. So there's a lot of room on this instance to accept a much heavier write workload. This second chart is the read replica on the primary cluster. Okay? So a very, very similar profile overall. We've got the bulk load, and then we've got the majority of the read traffic. For the bulk load, there is no CPU utilization on the reader because we're not doing any reads at this point in time. Nonetheless, the reader is scaling up and then dropping back down again. And this refers back to something Brad mentioned earlier, that this particular read replica has been configured as a failover target for the primary. And so as the primary scales up, the reader is following it. It's prepared to act as a failover target should the writer fail. Okay. So we see the reader scale up and then scale back down again. And then once again, as we drive a higher number of requests against the read replica, we see the CPU utilization go up because we're introducing more worker threads in order to service all of those requests. Now here we have a much higher utilization. It's 61% utilization. And I think that's about nearly 80 NCUs that we end up using at the peak of the traffic. And then the last chart here shows us that secondary cluster, which is in the EU West 2 region. Now, I introduced this secondary cluster after I'd done the bulk load. This is standard good practice. If you've got a big bulk load, tend to do that on your primary cluster before introducing any secondary regions. So what we've really got here is all of the read traffic against that secondary cluster during the regular workflow. The stuff that I'm particularly interested in, I'm going to remove some of the detail here. What I'm particularly interested in is this global DB progress lag. So this is one of those metrics that we give you that shows how data is being replicated or how quickly data is being replicated from the primary cluster to the secondary cluster. And you'll notice that when we don't have any particular write workload on the primary, we've got that period of idleness where we're not issuing any writes whatsoever, the progress lag is in the order of about 400 milliseconds. But we're not doing any work, but it's a reasonably high progress lag. But the moment the write workload kicks in and we start issuing all of those writes against the writer in the primary region or the primary cluster, that replica lag or that progress lag drops to, it's about 85 milliseconds. So it's consistently under 100 milliseconds for the duration of that heavy write workload. And then once the writer is idle again, the progress lag goes up. And this is pretty standard for Neptune serverless. You know, when there's not any work going on, all we have are synthetic heartbeat writes from the primary to the secondary region. That's what's driving the high progress lag. But at the moment, we've got a very high write workload. We're replicating very, very quickly and typically under 100 milliseconds. Okay. So that's giving you some sense of how to create serverless, how to create a global database. We've looked at a sample application, the fraud detection application. We've looked at some of those productivity tools. And then we've looked at some of the metrics for the way in which all of that behaves. So that's pretty much the end of that demo. So just hand back to Brad.
So we can just swap back for the last couple. So if you're interested in learning more about graphs and graph applications, there's a couple of related sessions tomorrow. It looks like they're heavily concentrated at the MGM Grand. I just wanted to point out to folks if they're interested. We have a number of different resources to help you learn about serverless, learn about OpenCipher, learn about global databases, learn about just how to get started, or even how to get started for free with the free trial. And so I'd invite you to check those out if you're interested. And thank you. Thanks for taking the time to spend with us. I know that there's a lot of things competing for your interest here at reInvent, and we're glad that you chose Neptune and Neptune Serverless. And as I've said throughout, we'd love to hear from you. My email's there, Ian's email's there. We have a couple of other ways throughout there. So let us know how things are.